So, ladies and gentlemen, the next talk is a good example of international cooperation on which Eli is based on, because there will be actually two parts. In the first part I will give some introduction about photoacoustic, and then I switched on the table and Simona will talk about the very exciting biological application of the photoacoustic method. So just to give some, before giving some introduction about photoacoustic, let me introduce myself. I'm actually working on photoacoustics since 1992, so quite a long time, and I am the vice head of the research group on photoacoustic spectroscopy, which is co-financed by the Hungarian Academy of Science and the University of Szeged. And I also took part in the foundation of Highlands Limited, which is a spin-off company of the University of Szeged, and which develops and sells photoacoustic analyzers for new applications. And so, outline of my presentation, I will talk about the photoacoustic effect. I will explain you how to build a photoacoustic detection system, so at the end of my talk you will be able to build a better photoacoustic system like we can do. And I will give just very simple basic equation of photoacoustic. I will give a comparison of the photoacoustic method with optical absorption spectroscopy, because it's always important to find the place of your method in comparison with the competing methods. And I will just give some examples of the application areas of the photoacoustic method what we are using. So the photoacoustic effect is very simple. So you have a gas volume in which you want to measure the concentration of the targeted molecule you are interested in. So you are illuminating this volume with a light source which is modulated in time, and also the wavelength of this light source is tuned to an absorption line of the molecule you want to detect. So due to this illumination, the radiation is absorbed by the molecule, and this causes these molecules to be excited from the ground state to an excited state, and then this molecule will relax non-radiatively, so without emitting light, back to the ground state, and they will release the absorbed energy. And this absorbed and released energy generates a temperature increase in the gas. And this periodical temperature increase in the gas will be periodic, because you are modulating the light periodically, and this periodic temperature change via thermal expansion will generate an acoustic signal. It will generate an outgoing acoustic wave, which you can detect with a sensitive microphone attached to the volume you are illuminating through. So this is a very simple picture about the excitation, the photoacoustic effect. There is absorption of the modulated light, which causes periodic excitation of the absorbing molecules. You will have a non-radiative relaxation, which causes the increased kinetic energy in the illuminated volume, and this increased energy of the molecules is actually increased temperature. So you will have a temperature variation. So absorption of the modulated light causes a periodic pressure variation, which is sound. And so this is the photoacoustic principle, and basic photoacoustic setup what we are using is very simple. So you have the photoacoustic cell, a closed volume, you have a continuous gas flow through this cell, illuminated by a laser which is tuned to an absorption line of the detected molecule, and it's periodically modulated. And you have a microphone in the middle of the cell which senses this pressure variation, and then with the appropriate electronics you can control the laser, you can measure the microphone signal, and you can calculate the photoacoustic signal, which will be in relation with the concentration of the measured molecules. So what are the advantages of the photoacoustic method? First of all, it's a direct in situ measurement. So you can see that, the gas to be detected is directly measured in the gaseous phase. There is no chemical reaction, there is no adsorption effect. It's a direct measurement of the molecules. Second, it has a high sensitivity. I will talk about it later. And there is a good selectivity, which means that if you have a proper light source and you are operating it in a proper wavelength, you can ensure that only that component which you want to measure is generate the acoustic signal. So you can, in a complicated gas mixture, you can make a selective measurement of the targeted molecule. The photoacoustic also has a wide dynamic range because of the applied acoustic detection. So 5 or 6 order of magnitude concentration variations can be detected with the photoacoustic method. It's also a fast response system because the volume of the photoacoustic cell is small. You have a continuous gas flow. That means that if the concentration is changing, your system is responding fast. So you have temperature response time in a second range, 1 or 2 seconds range. It's very important that this is a zero background measurement method, which means that if you do not have a light absorption, then there is no photoacoustic signal is generated. It's a unique advantage, or quite, I'm not saying that unique, but it's a big advantage that no measured component means zero signal. So there are frequently asked questions about the photoacoustic method. First of all, what is the photoacoustic signal? The answer is that the photoacoustic signal is the amplitude of the microphone signal variation at the frequency of laser modulation. So you modulate the laser, let's say at 4 kHz rate, and you detect the microphone signal, and you are searching for the microphone signal variation exactly at the frequency of the laser modulation. This is and the amplitude of this microphone signal variation is the so-called photoacoustic signal. Next question is, what makes the photoacoustic method selective? Selectivity is coming from the laser, which is tuned to the absorption line of the targeted molecule. So it's not the frequency. The frequency is dependent on the signal. The photoacoustic signal frequency is dependent on the laser modulation frequency. So this is not so that water vapor has different frequency than methane, but actually the laser which is making the photoacoustic method selective, the laser wavelength. Now, the related question, are different components generate photoacoustic signal at different frequencies? No. Photoacoustic, the frequency is solely dictated by the laser modulation. So the laser, so as I said, water vapor and methane does not generate different frequency acoustic signal. The next question is why we need to apply a special so-called lock-in detection. The answer is that the photoacoustic signal is weak. It's sometimes in the nanovolt region, or if you talk about acoustic amplitude, then it's a micropascal region. So there is a need to amplify the photoacoustic signal, and this amplification has to be selective, meaning that the environmental noise, which is also sensed by the microphone, has to be suppressed, while and in parallel the photoacoustic signal has to be amplified. Yes, and the photoacoustic signal is almost truly background free, but if you have some light absorption on the windows of the photoacoustic cell, this might generate some photoacoustic signal. So some historical background that the photoacoustic effect was discovered by Abraham Graham Bell in 1991. Here you can see the original setup. He was using with sunlight focused on absorbing target, and the wheel was turning, which chopped the incoming light, and he was listening to the generated acoustic signal. I will not talk about it, but the photoacoustic signal can be generated not only in gases, but also if you illuminate the liquid or you illuminate solids, it also generates photoacoustic signal. So there are photoacoustic measurement for liquids and solids too. And not only periodically modulated light can be used for photoacoustic signal generation, but for example, pulse laser are also generating photoacoustic signal. An important point that in principle it gives information not only about the optical properties, the optical absorption coefficient of the sample, but also about the thermal and acoustical properties of the sample. The photoacoustic effect also gives information. So if you see historically, after its discovery in 1881, it took some time before photoacoustic was widely accepted, but in the last century, in 1960s and 1970s, the photoacoustic method was really booming, and there were a lot of publications because people applied carbon monoxide and carbon dioxide lasers, which were very powerful, with which one can access the fundamental vibrations in the mid-infrared. So really people could measure that with ppb or ppt sensitivities. But later it turned out that these lasers are pretty complicated to operate, so we didn't go into that direction of these lasers, but we wanted to build a photoacoustic system which has automatic operation and which has outstanding reliability. So how to build a photoacoustic gas detection system? If you have a problem, somebody asks you to measure a certain gas component, how do you start to build a photoacoustic system? First of all, you go for a spectral database, and you are searching for a strong absorption line of the targeted molecules, and hopefully with minimum spectral interference from other components which are also present or might be present in the gas you want to measure. Then if you know the absorption line, then you are looking for for a laser which is easy to handle, which preferably emit in a single mode, which can be modulated and which can be tuned to the selected absorption line. And you direct this laser through the photoacoustic cell. And then you ensure that the gas you want to measure is purged through the photoacoustic cell. And then you start to modulate the laser, and the laser modulation is set to an appropriate acoustic resonance frequency of the laser. And then you have to apply a lock-in detection technique which filters the useful signal out from the wideband acoustic noise. And finally you have to calibrate the system with known concentration, and once you have the calibration constant, you can program your photoacoustic system for long-term automatic operation. So actually it sounds quite simple, but there are of course details which has to be taken into account. So here is the photoacoustic system, as I said, and as a laser light source we are using a telecommunication type near-infrared lasers operated at room temperature, fiber coupled, and they have a single emission mode. These lasers, because they are from the telecommunication industry, they have extremely high reliability, they have lifetime more than 10 years, they can work without problem. So these lasers are not very powerful. The output light power is between 20 and 120 milliwatt, and the wavelength of these lasers can be tuned by changing the temperature of the laser, which is quite easy to do, and it's also easy to modulate these lasers by modulating the driving current of this laser. And I skip these frequently asked questions because I do not have too much time left. So the photoacoustic cell we are using, and the microphone which is attached to our photoacoustic cell. So this is a 10 centimeter long acoustic resonator, approximately 10 centimeter long, which has an acoustic resonance at around 4 kilohertz, which is a very nice frequency. It's really in the audible range, so we have very good microphones for that, and there are not too big noises in the 4 kilohertz frequency range. These are low quality factor resonances, so it's not a very sharp acoustic resonance, which means that the laser modulation frequency is relatively easy to keep on the top of the resonance frequency. The photoacoustic cell has a special construction, special volumes inside. These are serving to suppress external noises. And the useful volume inside the photoacoustic cell is only a few cubic centimeter, and under a continuous gas flow, this has a response time only a few seconds, as I said. And it's also because when the light is going through the photoacoustic cell, it suffers negligible absorption, which means that after the first cell, one can put a second cell and measure in a second photoacoustic cell. So duplicate the detection cells, it can be done easily. And the microphone we are using is a very robust hearing aid microphone, and it has a negligible long-term variation in the sensitivity, so also a very reliable system. And then we have the electronics of the, we are using, it's a highly integrated electronics, and it can control up to 3 lasers and 5 detection cells simultaneously, and the electronics is capable to perform various self-checking and self-correction algorithm. It can search for the wavelength, the proper wavelength of the laser. It can search for the proper resonance frequency. It can detect if the outside noise is too big, which means that the system is overloaded by noise. So it has really various self-checking and self-correcting algorithm. And various form, we have this electronics that either in a, it can operate in a standalone mode, or it can be connected to a computer which processes the signal, and various data transfer and communication protocols can be used. And the gas handling of the system, I think I skip also this. It's a critical part of the system. Let's switch just very briefly to the basic equation of photoacoustic. So the photoacoustic signal is equal to this is the microphone signal in millivolt, is equal to the following expression. P is the light power in milliwatt, M is the microphone sensitivity, meaning that 1 Pascal, how many millivolt is generated by 1 Pascal acoustic signal, and C is the cell constant, which means that the efficiency of the photoacoustic signal generation by gas phase light absorption. So this is the construction. This expresses the construction of the photoacoustic cell. So how efficiently the absorbed light energy is converted into acoustic signal. This is the cell constant, and alpha is the optical absorption coefficient of the targeted molecule of a unit concentration, and C is the concentration of the gas component. So you can, and R is some background signal due to window absorption. So as you can see that photoacoustic signal is really proportional to the concentration. It's better to use higher light power. It's better to use a more sensitive microphone. It's better to use better cell construction, and it's preferable to operate the system at a strong absorption line. And all these together will define the photoacoustic signal. So a very simple expression. I'm also skipping that how to determine the noise, the sensitivity, the minimum detectable coefficient. This is just basic chemistry, analytical chemistry, what is here, so no problem of skipping this. And the frequently asked questions. So what, when I started to do photoacoustic, and after we developed the photoacoustic method, the question was that, how our photoacoustic system compares to competing measurement technique. And natural choice of comparison is the optical absorption spectroscopy. When you have a light source, you put the sample in front of the light source, and you are measuring the attenuation of the light after this sample. It is based on the Beer-Lambert law. So what we did is we took a photoacoustic system, the cell, the laser, and so on, and compared it with a state-of-the-art optical absorption system with a multiple reflection system, a multipath system, and it's a big and very carefully optimized optical absorption system. We made a comparison, and this is a measurement result which I made at the Rice University at Houston when I compared the photoacoustic system with the optical absorption system, and you can see that the photoacoustic is responding, this black is responding faster than the optical absorption system. So the photoacoustic is faster, and if you compare the background, the noise of the two methods, then you can see that the photoacoustic is less noisy than the optical absorption system, and otherwise they are giving very similar results. So this was just a 2 weeks measurement campaign, but it was for me it was very persuading that our photoacoustic method is really capable to give somewhat better results than the commonly used optical absorption method. So that was in the following, it was a good feeling that I can really trust in the photoacoustic detection method. So these are what we learned from the intercomparison, which these facts that better repeatability of the photoacoustic, shorter response time, more robust photoacoustic system is made us confident about the photoacoustic method. And I have only a few minutes before I finish, so let me just give our application of the photoacoustic method, what we are doing here at Szeged. So our main application, our main success story was to measure for the oil and natural gas industry, to measure hydrogen sulfide, carbon dioxide, and water vapor concentration in gas streams. And then we measured gas permeability of sheet polymer samples, and we have also airborne measurement of atmospheric water and total water, and we are also busy with aerosol, atmospheric aerosol measurement. So here you can see that in the oil and gas industry is really using our photoacoustic method for various applications, and it's a very robust technique, long-term operation. I think if something is working in the oil and gas industry, then it's really a robust measurement technique. We have instruments which are working on offshore platforms for several years now. So I think this is proving the reliability of the photoacoustic method. A lot of applications with various gas handling. And this gas permeability measurement, so if you have a sheet sample and you are putting 100% of water vapor and H2S or whatever of these components, you can see how these gases are diffusing through your sample, and this you can detect with a photoacoustic system, and what you will get is such a nice permeation curve. So at the end of the measurement, you have nothing in the receiving chamber. You have nothing here. You have 100% methane, for example, here, and nothing here. But as the time is elapsing, gradually you can see that appearance of these molecules as they are diffusing through the sample. And we made a lot of variants of this detection method. And we were also able to put our photoacoustic system into an airplane, and on a commercial airplane. And there is, in the Caribbean project, it's a big German project, and they are using 1.5 ton instrument rack for measuring a lot of components in the atmosphere during flight. And our photoacoustic system is there for measuring water vapor and total water in the atmosphere. And it's operating, I think now it's almost 10 years without problem, and showing and measuring continuously the water vapor and the total water of the atmosphere, which is a very important parameter for climate research and modeling. So, and then we have the aerosol measurement, but I do not want really to go into the details. So what I can say that a carefully designed and operated photoacoustic system is a powerful tool in many applications. And into one photoacoustic instrument, you can actually put several lasers, several detection cells. So one instrument can act as a multiple instrument actually. And as far as I see, the outstanding advantage of the photoacoustic method is the long-term, fully automatic, trouble-free operation. So with this, I thank you for your attention, and I ask Simon to talk about their application of the photoacoustic technique. Thank you very much. If you have any question during the time of switching the laptops.
Is your device can be used online? I mean,
yes.
Go through and online.
Yes. Real-time online detection, continuous monitoring without delay. Real-time delay. Yes, you are right. This is a big advantage. Maybe I not emphasize.